Good morning. This is lecture 19 on fractional factorial designs. I would just want to repeat that if there are questions, please post them to the discussion board where I and or the rest of the class can answer. This is the first of what I expect will be 2 lectures. I'm hoping that lecture 20 on Monday the 11th we would use to answer questions and review some of the examples that are given in this lecture. Very briefly, we'll cover questions and review as we have done each lecture since the beginning of the class. The bulk of the material today is on 2-level fractional factorial designs, and even briefer is 2 examples on using an R function, FRF2, which one would use to design fractional factorial experiments, and the output from FRF2 is the design matrix that you would use. Since there are no questions, we'll just briefly review the schedule. This is the first online lecture for the remainder of the semester. On the 11th, we will continue with fractional factorial designs, and then into mixed level designs, and then finally the last 2 subjects, response surface methods and Taguchi designs. But let's begin with fractional factorial designs. Now there are 2 things that I will leave you with and that motivate or give you a philosophy for why we pursue these. One is the idea that we can reduce the number of experimental runs but preserve to as high a degree as possible the effects that we're trying to measure. Right? We know by now that the number of experimental runs in a factorial design where each factor has 2 levels grows exponentially with the number of factors. Now this could easily get out of hand very fast, and while it may be a simple design conceptually, it can be very costly. The purpose of exploring fractional factorial designs is that we're looking for a way of reducing that cost, reducing the number of experimental runs, while preserving our ability to maintain a relatively easily conceptual design, or conceptually easy design, but reduce the cost. The underlying principle of measuring main effects or factor interactions in a fractional factorial design is based on the principles of confounding and blocking, as was given in Monday's lecture, that previous lecture on the 4th. So you may want to review the slides at this point. You might want to pause the video and return and take a quick look at confounding or blocking, or at least have those available to you as you're proceeding through this lecture. Now, in fractional factorial designs, if you are trying to measure main effects, and only main effects, you need only 2 blocks. You have a set of experimental runs with the factor of interest at the high level. You have another set of experimental runs with the factor of interest at the low level. You compute the average in each group, and then you take the difference, and that gives you a measure of the main effect for a given variable. Conceptually very easy. But the problem is that you have confounding, that that same design will also measure interaction effects between other variables. So if you have a set of 3 or maybe a set of 4, as you'll see examples later on, the main effects are confounded with interaction effects in the experimental design. Now if we're only interested in main effects, that's of no consequence. And as we've done with analysis of variance problems earlier in the semester, we will ignore the effects. They are of no consequence. However, be aware that they do exist. In a fractional design, the same thing can happen. That is, when you measure main effects, as you'll see, they're confounded with the interaction effects from other variables, and we'll refer to this as aliasing later on. And this is, this is a trade-off between the number of experiments and the power of the experiment. So remember, our definition of power is that we correctly reject the null hypothesis if it is in fact false. Well, if you have aliasing, that is, if you have confounding between the effects, you're not going to measure the effect accurately, and you may not, in fact, reject the null hypothesis when it is, in fact, not true. So this is a trade-off that you will make, and it's a typical engineering kind of trade-off, and you have to choose the optimal situation. And the trade-off is this, that if there are fewer experiments, you're going to have more confounding effects. If you want to resolve main effects, and if you want to resolve two-factor interactions, or if you have 3 or more variables and you want to resolve 3-factor interactions, then you will need more experimental run. But that's a trade-off that only you can make, and it'll be based on the hypothesis you're trying to test, and it will be based on the experimental design that you choose. Well, we'll start with the hypothesis, and you need to select the hypothesis test or the appropriate test or the test statistic, and determine what is the best way of achieving a test statistic that will reflect the underlying difference between the groups, and that will give you the optimal experiment. Now, in fractional factorial designs, we're not really talking yet about optimal experiments. We'll get to that when we study response surface methods. The search for an optimal experiment is not random. You don't just mess around until you find the experiment, or I hope that you won't do that in your own research. But what I hope to leave you with here is that there's a rigorous approach, and it's an algorithmic approach. There's a sequence of steps that you can follow in order to design an optimal experiment. If it was a random search, we wouldn't be able to have software or functions in R that will give you the design matrix. And as you'll see at the end of the lecture, there's a very systematic way of specifying the number of variables, the types of interactions that you want to measure, and the function will generate the design matrix. But let's begin with some background information on fractional factorial designs. As I said earlier, if you have k factors, and since they are all at 2 levels, you have 2 to the k experimental runs in your experiment, and we'll call the number of experimental runs the cost. It's obvious to all of us that the cost of an experiment increases exponentially in k, because the number of runs is given by 2 to the k. Now, one of the key assumptions that we're going to make in order to develop a fractional design is that if there are high-order interactions that are not of interest, or that they're not of consequence, or that I can neglect them for some reason, that they're not really part of the hypothesis testing that I want to perform, then I only need to worry about main effects and possibly low-order interactions. And what we'll leave you with today is some examples showing you that you only need a fraction of the complete experiment in order to measure the main effects and low-order interactions. Now, these are some of the most widely used designs because you minimize the number of experimental runs that you have to use, but it's also the case, and perhaps more importantly for many of you, is that you can use these as screening experiments. You use these as pilot experiments and preliminary experiments, as I referred to them earlier, and you can use these simply to measure the main effects or low-order interactions. And once you identify the factors of interest, then you can design an experiment that is optimal to test those main effects of interest. Here are some of the key assumptions in the design of fractional factorial experiments. Again, just keep in mind that You can use a fractional design if you're only interested in, or if you believe that it's only main effects of each factor independently, and there's low order interactions, possibly two-factor interactions, but presumably nothing more. If you start with a complete factorial design, what you'll find is that the fractional design turns out to be a subset of the complete factorial design. That is, and they use the term here, projection, is that what you'll see is that the fractional factorial design can be inserted or projected onto the complete factorial design. It's a subset of the experimental runs. Now, the other thing that you can do is run two or more fractional designs in sequence. If we use what we'll refer to as the 1/2 fraction, that is 1/2 of the experimental runs, then a complete factorial design can be used to generate two 1/2 fraction designs that I can run sequentially. So I could run a 1/2 fraction design, measure the main effects, and if necessary, run the other 1/2 fraction. So let's look at that first case. The simplest is the 1/2 fraction. That is, it's 1/2 of the 2 to the k designs. And in a 1/2 fraction, there are 1/2 of the experimental runs in a full factorial design. So if there are 3 factors, each at 2 levels, there's 8 runs. In a 1/2 fraction, we have 4 experimental runs. That's written as you see 2 to the 3 minus 1. 2 to the 3 representing the full factorial design, and 2 to the minus 1, of course, is 1/2. And so 2 to the minus 1 times 2 to the 3 is 1/2 of the 8 experimental runs, so we write it as 2 to the 3 minus 1. And this is a notation you'll see throughout the remainder of the course and any of the literature that you'll read on experimental design of fractional factorials. Now, the runs that you choose for the fractional factorial design are not chosen arbitrarily. There's well-defined rules that we will use to select the runs, the subset of the runs from the full factorial design. And those are chosen using what's referred to as the defining relationship. And remember that we've used a couple of different ways of annotating 2 levels of a factorial design, sometimes a 0 and a 1, sometimes a -1 for low and a +1 for high. And what you'll see in the material in today's lecture is that we're going to use a plus and a minus. So the minus represents the low level, and the plus represents the high level. So the design matrix will be full of pluses and minuses. And in the case that we'll consider first, we have 3 factors, that the factors will be called A, B, and C, and the product of the factors will be termed what we call the generator of the fraction. And generator in this sense means the annotation that we use or the way that we determine which runs are included in the 1/2 fraction. So let's continue. Here's an example of a design matrix for a 2 to the 3. That is a full factorial design. This is again an example from Montgomery. If you go look it up, there'll be some additional text, but I think that you can see relatively easy the design matrix, and that's given in the columns A, B, and C, so that in the first row, A is assigned the high level and B and C are assigned the low level. I'll attempt to highlight those with the mouse. So these 3 rows that I'm encircling are the elements of the design matrix. I have 3 factors, and you can see there are 8 rows for eight experimental runs. In the first experimental run, A is assigned high and B and C are low. In the second, A is low, B is high, C is low, and you can follow the rest down. There are several other columns in this matrix that are not part of the traditional design matrix, but they represent factor interactions, or as we've noted here, factorial effect. The first column, I, represents the case where all 3 factors are low, and you'll see that in the graphical representation. And the last 4 columns represent the factor interactions. And so you simply get these by multiplying the annotation for the individual factors. So for example, the column that I'm pointing to now is AB, so it's the 2-factor interaction of A and B, and in the first case it's shown as a negative, and that's because I assign a high level to A and a low level to B. The product of the 2 is negative, meaning in this experimental run with this assignment to the factors A, B, and C, the factor interaction AB is at the low level. And so the first 2 are low, the next 3 are high, and the last, well, these second to the last 2 and the third to the last are low, and the last case where I have the case where they're all negative or at the low level is AB is positive, of course. Now we refer to ABC, the product of ABC, as the defining relationship for the fractional factorial design, and the experimental runs that we select for the 1/2 fraction of this 2 to the 3 design are the 4 experimental runs, remember that's 1/2 of the 8, where the defining relation ABC is positive, and that happens to be the first 4 runs, these, as I'm circling, as you can see. So that's the case where A is high and B, C are low, A is low, B high, C low, A low, B low, C high, and A, B, C are all high. So those are the 4 experimental runs in the 1/2 fraction of the 2 to 3 full factorial design. So here's a graphical depiction of the 1/2 fraction design. You see in the cube that's on the left the 4 experimental runs that are highlighted with the dots show first where A is high and BC is low, B is high and AC is low, C high, AB are low, and ABC, they're all at the high level. So that's using the defining relationship ABC, as you can see. The alternate fraction, which means the other 1/2 fraction, are where the defining relationship is not positive, but they're negative. And I'll briefly go back to the previous slide, and you can see that those are the last 4 cases. So let's pick the 5th row where A is high, B is high, and C is low. That is, A is high and B is high and C is low is the one that I'm circling over on the right-hand edge of the slide. So we'll refer to this as the alternate fraction. So these experimental runs are mutually exclusive with the set that's on the left. They together, the 2 1/2 fractions, form the full factorial design. And as I mentioned earlier, if I first did the fractional design that's on the left, I could follow it sequentially with the fractional design on the right and form the full factorial relationship. Now our interest, of course, is in the main effects and low-order interactions. Our motivation to begin with was that I did not need complete factor interactions, that I believe that we only need to measure main effects and the interactions at in this case at the two-order, two-factor interaction level. But here's how we'll measure the main effects for this 1/2 of the 2 to the k design, or in our case 2 to the 3 design. So the main effect A is measured by adding 2, not 4, but adding 2 experimental, the response variables, that's 2 experimental runs. As you can see, the case where A, B, C are all high has A high, and the experimental run where A is high, B is low, and C is low, and also will have a positive effect. So here's ABC where A is high. Here's A where A is high and the other 2 are low. But because B and C are low, we consider that to be a case where B and C interact because they're the same. So A plus ABC are cases where A is high and the other 2 have no effect. Now in the remaining 2 runs, as you can see, where minus B and minus C, B and C are at opposite levels. So in the first case, B is high and C is low, and the second case, B is low and C is high. So these are 2 cases where A is low, and so we'll subtract those. So as we did in measuring the main effects earlier, we take the average of the cases where the factor level is high and subtract where the factor level is low. So that's 1/2 of the relationship that you see. In the second case, of course, you see the slight difference. ABC has B high. The second case is B high. So we have 2 cases where B high, and then the other 2 cases, minus A, minus C, where B is at the low level. And when I add the 2 and then subtract the difference, take the average, that's a measurement of the main effect of B. And in C, ABC has C high, C has C high, minus A, minus B both have C low. And so when I add the first 2 and I subtract the last 2, I'm referring to, of course, the response variables for these experimental runs, I measure the main effect of C. So these are the defining relationships for measuring the main effects of the 3 variables A, B, and C using the fractional factorial design. In fact, specifically, this is the 1/2 fraction of the 2 to the 3 design. Now, possibly we'll measure also 2-factor interactions, but not a 3-factor interaction in this case. And here are the defining relationships for the 2-factor interaction effects. Now, I started to allude to these when I was describing main effects, but let's review this briefly. That in the case of where ABC is all high, the last of the 4 terms, that has a case where B and C both have the same assignment. So this is one of the positive response variables where B and C could possibly interact. And I'm going to argue that the first case, A, is similar. It's similar in the sense that B and C have the same level, although in this case B and C have the level low. So ABC is A high, BC high. The first case is A high, BC low, but BC low being the same, they could possibly have an interaction effect because they were assigned the same level. And so ABC plus A are cases where there's possibly a positive interaction. And in the other 2 cases, minus B minus C is a negative interaction because one of them is high, B then C, and the other is low, C then B. So positive interaction minus the negative interaction, take the average, and you measure the 2-factor interaction effect, that is BC. And similarly, AC and AB are measured the same way. We'll be using in the rest of this section on factor interactions and mixed level designs the square bracket notation to refer to main effects. if it's a single variable, interaction effects if it's two or more notations for the variables. Let's move on. This shows the situation graphically that we were talking about on the last slide. Once again, you see the cubes representing the three factors A, B, and C. The principal fraction using the defining relation positive ABC is shown on the left. The alternate fraction with the defining relationship negative ABC is shown on the right. Now I'm going to briefly turn back to the previous slide to talk about the interaction effect, and you'll notice that for the defining relationship for the main effect A is 1/2 A minus B minus C plus ABC. The defining relationship for the two-factor interaction effect BC is the same, 1/2 A minus B minus C plus AB. And that's because of the relationship between the two factors happens to be the same as the A. Now suppose that I compute the main effect A. It happens to measure the main effect of the first factor A, but I'm also measuring the interaction effect BC. So that if I measure the main effect A, it's A confounded with BC. Measure the main effect B, it's the effect of the factor B confounded with the two-factor interaction AC. And when I measure the main effect, or rather compute the main effect of the variable C, it measures the effect of C, the factor C, as well as the two-factor interaction AB. So each of these main effects are confounded in some way. This property we'll refer to as aliasing. That is, these two effects are aliased, and I can't separate the two. This is the price you pay for a fractional design. You're reducing the number of runs, you're reducing the cost, but you're confounding or aliasing two-factor interactions with the main effects. So there's an additional piece of notation that we use in the field, in the design of experiments, to describe which factor interactions are aliased and which are not. So we'll extend the notation as you see here, where 2 to the 3 minus 1 represents, or as we know now, a three-factor factorial design. The minus 1 indicates that it's a fractional design. In fact, it's a 1/2 fraction. But you'll see there's a Roman numeral now in the subscript. And the Roman numeral in the subscript refers to what we're going to call the design resolution. And you ought to think about resolution in the sense of what we can resolve, what we can separate out by the design. The higher the resolution, the closer you're looking at the response variables, the closer you're looking at factor interactions, and the less restrictive the assumptions that are required to determine which interactions can be neglected. In a resolution 3 design, no main effect is aliased with any other main effect. Okay, so we see that in the example that we just did, 3 factors, 1/2 resolution. In a resolution 3 design, it's also the case that main effects are aliased with two-factor interactions, which we saw. And I'm going to go back a slide previously just to remind you that when I measure the main effects for A, B, and C, that the main effect for A measures the effect of the factor A, but that's aliased with the two-factor interaction BC. Right, so the definition for a resolution 3 design is that no main effects are aliased, but main effects are aliased with two-factor interactions. The notation for that is 2, because we have 2 levels to the 3, so K is 3, I have 3 factors, minus 1 is a 1/2 fraction, and subscript Roman numeral 3 means a resolution 3 design. This is one of three that we'll typically use or that satisfy most cases. The second is a resolution 4, and here's the definition: that no main effect is aliased with any other main effect or with any two-factor interaction. So again, if you go back one slide, you'll see that those definitions don't apply here, that I do have an aliasing effect of main effects with two-factor interactions. So the design we gave you is not resolution 4. But in a resolution 4 design, two-factor interactions may be aliased with other two-factor interactions. No main effect is aliased with two-factor interactions, so that could be nice if you want to measure only main effects. But two-factor interactions are aliased, and that you could live with if you're not interested or you believe that there is no two-factor interactions in the experiment you're trying to run. So the notation here has a subscript 4. A resolution 5 design, and no main effect or two-factor are aliased, but two-factor interactions may be aliased with three-factor interactions. If you believe that three-factor interactions have little to no effect, then you may be able to construct a resolution 5 design. The notation, of course, has a subscript 5 rather than the subscript 4. Now, there's one other thing that you'll notice, and in that as you move from resolution 3 to resolution 4 to resolution 5, in order to gather better resolution information on the main effects or two-factor interactions, that you need more experimental runs. So I can achieve a resolution 3 design with a 2 to the 3 design, and resolution 4 with 4, and resolution 5 with 5 factors. So here's how we construct the 1/2 fraction. Now, we went through a case before, but let's simply review that. And this is a general methodology, slightly different than what we did before, but we present it this way so that you can construct it with the knowledge of the design resolution in place, okay? Unlike the initial case that we did. So we're going to start with a subset of a design. So let's assume that I have 3 factors, each at 2 levels, so the full factorial design is 2 to the 3. I'm interested in constructing a 1/2 fraction, which would mean 4 experimental runs. Now, I'm trying to construct a design matrix, which means I'm trying to construct the matrix that has the assignments to each of the factors for each of the experimental runs, which are shown as 1, 2, 3, and 4. What you will start with is a full factorial design for 1 fewer factors. So if I have, if I'm interested in a 1/2 fraction of a design with 3 factors, I'll start with a full factorial design for one with 2 factors, as you see in the first 2 rows, the first 2 columns on the left-hand side. So in the first run, A and B are both low. In the second run, A is high, B is low, and you see the reverse. And then in the last run, A is high and B is high. So this is a full factorial design if I only had 2 factors. The next step is to add the 3rd factor. And you see 2 ways of doing it. In the first case, it uses the defining relationship where C is equal to AB, the interaction AB, the product of the 2. So then I have my 3 factors. Or the alternate fraction where I have C is equal to minus AB. So I literally take the product of the 2. So here C is high because A and B are both low, and a negative times a negative gives me a positive. In the intermediate 2 rows, C is negative, that is it is assigned the low level based on the fact that A is high and C is low, or the reverse, so that the product of these two, plus times minus or minus times plus, yields the negative, so that C is assigned a low level, and the last two obviously is the plus. In the alternate fraction, that is the last three rows that you see we're underlining right here, I use the defining relation, a negative AB. So the design procedure is you start with a full fractional design for the one fewer variable, and then you add the variable based on a defining relationship, as you see that's given, and simply multiplying them out as you could easily do with an algorithmic procedure, and then assign the factor levels either low or high as we've done. So this is a basic design of the runs for a 1/2 fraction design. And you start with a full 2 to the k minus 1 design, and then add the kth factor by identifying its levels with the highest order interactions. And the reason for doing the highest order interactions is that you push them out. So you'll see there's confounding here, so that when I measure the main effect of A, I'll measure a two-factor interaction, but I'll clearly have separated the main effects of the three variables A, B, and C. Whoops. So here's an example that will begin in just a moment. Before we move on to the example, let's take another quick look at the design chart that you see here. If you go back a few slides when you have a chance to take a look at it, you remember that the equation for measuring the main effect A was A minus B minus C plus ABC. And if we look at the 2 to the 3 minus 1 resolution 3 design, this is A plus ABC minus B minus C. And you can see by looking at that design matrix that this is not confounded with any other main effect, that the main effect of A is definitely separate from the main effect of B or C, but also separate from any two-factor interaction, except for the BC case. Okay? And we say that because A plus ABC has one case where both B and C are high and B and C are low, so that there's interaction between the two, and the other two cases are opposite, so that by inspection of this design matrix you can see that A is confounded only with the two-factor interaction BC. Let's move on to the example, and then I'll finish up with a quick demonstration of using FRF2. So this is an example of filtration rate, and we're studying the factors that may influence filtration of a product. And so this might be something you find in chemistry or a chemical, engineering laboratory, or even bioreactors if you happen to be in the field. So a number of factors that may influence would be temperature, pressure, and so both of these influence flow, concentration of formaldehyde, and stirring rate. So there are 4 factors. If each of these was at 2 levels, you have 2 to the 4th, or 16 runs in the full factorial design. Now, again, let's assume that that's a lot. The generator is, of course, the product of the 4 factors, all at the high level. So that's A, B, C, D, and our goal is to use that generator to find the design matrix, which will yield the highest possible resolution, which in this case is resolution 4. So it's 1/2 fraction of a 2 to the 4th 16-run design resolution 4. So, here's the graphical depiction on the bottom. I see two cubes that represent the factors A, B, C, and the factor, the cube on the left is the cube where the fourth factor D is low, and the cube on the right is where the fourth factor D is high. And each dot represents the experiment that's performed in the 1/2 fraction, and the number that's given there is the response variable, the value of the response variable, the filtration rate, which goes as high as 100 complete filtration down to a case where there's 45. So there are 8 runs in the 1/2 design, and remember that you start with the basic design of 3 factors, right, A, B, and C. It's one fewer factor. That the fourth factor is, the levels of the fourth factor are set using the defining relationship for the basic design. And so when you simply take the products of the negatives and the positives all together, you get the assignment to D. And then from these you can determine the treatment combination. So in the first case, all 4 are low, and that's what we define by the 1 in parentheses. And then there's 2 factor interactions, and then the last being A, B, C, D, where they're all high. The value of the response variable is shown on the right-hand side of table 8.3. Okay. Start with one fewer factor, the complete factorial design, use the defining relationship to set the value of the last factor, and then you can determine the aliasing effects by looking at the design matrix, the complete design matrix, and you can see the treatment combinations. So let's skip ahead and show you, and you can go back and convince yourself the values of the main effects of A, B, C, or D are shown in the left-hand side, 19, 1.5, 14, and 16, and then the values of the 2-factor interactions A, B, A, C, and A, D are also shown, and those are their actual numerical values from the combination. By looking at the design matrix on the previous slide, you can determine the alias structure. So when you measure the main effect A, A is aliased with B, C, and D very quickly. Then you can see that A, right, where A is higher, this, and these runs, and that's aliased with B, C, D. So here's a case where they're high. There should be a case where they're all low. Let's see, so it's BCD that we're looking at. So here's BCD is high, in this case where A is high. I think I might have an error in this case. Let's clarify the aliasing structure by taking a look back at the design matrix for this 1/2 fraction resolution 4 design with 4 factors. Remember that we start with the basic design for a 3-factor full factorial system. That's ABC. You see the matrix roughly on the left-hand side of the top graphic here, showing all 8 runs. And the defining relationship is A, B, C, D, meaning that the last factor, D, is the product of the 3 factors in the basic design, A, B, and C. We're using minus to represent low level, plus to represent the high level, and when you take the product of the 3, we get the values in the column that's labeled D. The treatment combination, of course, is a result from looking at the 4 columns A, B, C, D. In the first case, all are at the level low. we denote that by the 1 in parentheses. This, run number 2 has A high and D high, and so forth. I won't go through all of them, ending with the last case, A, B, C, D. The response variable. The filtration rate has the values in the very last column on the right. The experimental design is shown graphically at the bottom of the page. There are 4 runs with D is low, shown on the left. There are 4 runs with D on the high value, and that's shown on the right. And each of the experimental runs, the very dense circles, are shown with the values of response variable. Now, before we go on, I want to remind you of something, that this is a resolution 4 design, not a resolution 3. So in a resolution 4 design, there are no main effects that are aliased, and there are no main effects that are aliased with the 2-factor interactions. Secondly, that 2-factor interactions are aliased with each other. This means first, that the main effects are aliased with 3-factor interactions, and that we'll see an aliasing structure where 2-factor interactions are aliased with each other. So now I'll go once again to the next page, and we see the numerical estimates of the effects on the left-hand side. So the estimate of the main effect A is 19, B is 1.5, C 14, and D you see there. And then we have the 2-factor interactions AB, AC, AD shown in the calculated values given. Now, in a resolution 4 design, the main effects A, B, C, and D are aliased, but not with the 2-factor interactions. They're aliased with 3-factor interactions. So A is aliased with B, C, and D, meaning that when you try to measure the effect of A, you're also measuring the 3-factor, the effect of the 3-factor interaction B, C, and D. If we assume in this experiment that the 3-factor interaction is negligible, then this estimate 19 is the main effect of A. So the main effects A, B, and C, D are aliased with 3-factor interactions of the other variables, A with B, C, and D, B with A, C, and D, C with A, B, and D, and D with A, B, and C. In a resolution 4 design, 2-factor interactions are aliased with each other, and what we'll use the first as an example and go back to the design matrix. So in the aliasing structure, we see that measuring the effect of the 2-factor interaction AB is the same as measuring the 2-factor interaction of CD. We'll go back to the design matrix very briefly, and in the case of AB, the positive terms are A, B, C, D, AB, the case where they're all 0, and CD. Right, so these are the cases where both A and B have the same value, either high or either low. The other 4 cases, BC, AC, BD, and AD, are the experimental runs where A and B have opposite values. So the difference between those sets of 4 show the case where they're both the same, and you subtract from that the set where they're opposite, and that's a measurement of the effect of the 2-factor interaction AB. Now, if you happen to look at it, it'll turn out that that's exactly the same as the 2-factor interaction CD. ABCD also has C and D as both positive. A and B, where they're both high, has C and D as they're both low. The case where they're all low, the 1, has C and D low. And C and D here has C and D high. So those are all cases where they're both the same. And that's the same as the terms we used for AB. So you'll see, now if you work out the algebra, you should convince yourself that the effect of the 2-factor interaction AB is the same as that of the 2-factor interaction CD. So this aliasing structure we see satisfies the constraints of a resolution 4 design. No main effect is aliased with a two-factor interaction, but two-factor interactions are aliased with each other. Now, this graphic shows a three-factor design. It's related to the previous case, but it shows the factors A, C, and D. Now, we've left out B because you see the effect of B is very low, and the others are all about the same. So we conclude from this screening experiment, if you will, that the factor B is negligible or has negligible effect on the experiment where we're trying to measure filtration rate. Remember that B was pressure, so we're assuming that the effective temperature is high, the effective the formaldehyde concentration is high, and the stirring rate is high, but the effective pressure is very low, and so we can reconstruct or construct a different experiment leaving out the effective pressure, and it would look like this. Right, so temperature, concentration, and stirring rate. So the value of the screening experiment is that I can construct a optimized experiment in the sense I minimize the number of runs, but I can check for variables at the best possible resolution, including or primarily main effects, and we drop the variable of pressure because it has negligible effect. Now the next step is to construct the experiment you see here, which is a 3-factorial, full factorial design with the variables of temperature, or factors of temperature, concentration, and stirring rate. Now the examples that we've shown you so far that I've talked through have been done by hand, but it's not necessary that you do that. And the value, of course, of using R and the design of experiment packages is that you can do this for you. One such program to construct fractional factorial designs with 2 levels is FRF2. Okay? And FRF2 has a number of arguments. First, the number of runs in the experiment you're trying to construct, in this case 16. The number of factors in the experiment is 6. That's A, B, C, D, E, F. And then you specify the effects that you want to be able to measure without being aliased. In this case, we want to measure the main effects of the factors 1 through 5. That's what the first argument specifies here, rep 1 through 5. So I'm creating this vector 1 through 5. So I want to measure the main effects of A, B, C, D, and E. And then the second argument specifies that I want to measure the interaction effect, which I denote by the colon, of factors 2, B, and 6, F. So 5 main effects and 1 interaction effect. And the function generates a design matrix that you see. So this is not pluses and minuses, but the low value is denoted by a -1. The high value is denoted by a +1. Another way of specifying something similar is to actually name the factors in the formula of the effects that are estimable. So here we want to construct a design of 16 runs with 6 factors, and the formula specifies those factors that we want to be able to estimate without aliasing. So here we say A, B, and C, D, E, and F. So we want to specify the 6 factors and also the 2-factor interactions AB, as shown A colon B. Also the 2-factor interactions AC, AD, AE, and AF. So knowing the aliasing structure that one desires, you can determine the resolution of the experiment, and once I know the resolution and the number of factors and the number of runs, the experiment can be designed. Now, rather than we do it by hand, it's much easier for larger experiments to do it using the function FRF2 that's part of the Design of Experiments package. And with this, we'll conclude the lecture today on fractional factorial designs. If you have any questions, please post them to the appropriate place in the discussion board that refers to this lecture, lecture 19 on fractional factorial design for November 7th, 2013.